Hi, my name is Michael Healy, and today I'll be showing you my final project for Dr. Mitchell's remote sensing class. In short, remote sensing is the process of obtaining data about a specific target without actually physically coming into contact with it. There are two types of remote sensing, passive and active remote sensing. Passive sensing uses pre-existing sources, like the ambient light from the sun, to collect information. A common example of a passive sensor is the Ring doorbell system that uses a camera to detect when people approach your door. Active remote sensing is the process of sending out a signal, such as light or sound, and using the received signal to obtain data about certain objects. Examples of this are sonar, radar, and LiDAR. This project focuses on the use of LiDAR, which stands for light detection and ranging. LiDAR systems send out a pulsed laser signal and use the properties of the return signal to obtain depth information, also known as range data. This project also incorporates computer vision. Computer vision describes the use of computer programs to identify objects of interest, like people, road signs, and other cars, within a camera frame. Now that we've established our technical knowledge base, let's get back to the project. The goal of this project is to build an ever-growing 3D model of campus using student-built LiDAR systems. Each student picked out a different target from campus to scan and replicate in a 3D computer model. My target is this concrete stump located on the northwest corner of the administration building. There are numerous stumps like this lining Regents Drive outside the administration building as a way to block cars from coming off the road. I chose this target because it is a manageable size. It contains some details like the indent shown about 2/3 of the way up, and the surrounding area is fairly open, which would make data collection fairly simple. In order to scan my target, I built this LiDAR sensor. At the heart of it is the 3D printed mount that Dr. Mitchell provided. Attached to it are this line laser, this Raspberry Pi plus camera, this old phone, and tripod attachment. The 3D printed mount was hot glued together and taped for reinforcement. The laser, phone, and Raspberry Pi plus camera were all attached with a combination of hot glue, zip ties, and command strips. In this setup, the red line laser here acts as the signal transmitter, and the Pi plus camera acts as the signal receiver. The phone command strip to the back provides angle of tilt, which is used during data collection, and the tripod attachment allows me to place the sensor on the tripod to get it to the correct height and have easy angle adjustment during data collection. When I brought my sensor into the field and attached it to the tripod, as shown here, I added a string with a weight to the end of it to mark the exact location on the ground of where the LiDAR sensor was. This would help me during the data collection process to make sure each scan was aligned properly, but more on that later. Using this LiDAR sensor to mount my target involved two steps. The first is shining the laser on the target and taking a picture with the camera. The second involved running that picture through a Python script that used computer vision to identify where the laser was on the target. I'll get more into the specifics of that later on in this video. This diagram shows how the governing equation for the calibration of this sensor can be derived. The camera and the laser both point parallel to each other and are separated by a fixed distance of h. The target is the distance d from both the camera and the laser. D can be found by dividing h by the tangent of theta. Theta is found using the position of the laser in the camera frame. This sensor was first calibrated with a single beam laser. A Python script using the OpenCV class tracked the position of a laser in a specified HSV range and output its pixel coordinates. I then plotted these pixel values versus distance from the camera, along with the theoretical pixel versus distance curve, adjusting the rho and RPC values to match the data from my sensor. I repeated this process with my line laser, taking pictures at various fixed distances from a wall. I replotted the data and repeated the rho and RPC adjustment process, giving me my final calibration values I could use for data collection. To take my data, I set up my tripod, plugged in my Pi to my laptop, and ran the data collection script. I entered the angle from my phone when prompted, and the script took the picture of the target. I took about 22 pictures per side and took pictures from 4 sides of the target. I marked on the ground where the sensor was located for each scan, using the string with the attached weight to guide my marker placement. After my first scan, I lined up the sensor with the previous place markers to ensure each set of data was orthogonal to each other. I faced a small issue leveling out the laser when scanning on the grassy side, due to uneven ground. I also ran into issues with the amount of lighting around the administration building. Increasing the camera's exposure to 5 seconds fixed this problem. The last issue I faced was a faulty angle measuring app. Occasionally, the angle shown on the phone would not change as I rotated the sensor, so I would have to reset the app on the phone before continuing data collection. Once I had taken all of the pictures that I needed for all 4 sides of the target, I was able to run this data generation Python script. It uses HSV thresholding to identify the position of the laser in all of the pictures and output X, Y, and Z coordinates for all of the points where it hits the target. I ran this script 4 times, once for each of the sides of the target, adjusting the HSV values shown here for each side. I updated the row and RPC values for my calibration as mentioned earlier, and ran this script. For each of the 4 sides, it put out its own text file containing all of the X, Y, and Z points that it found in all of the pictures. I then read those coordinates into MATLAB and used simple matrix manipulation to get all sets of data in the same coordinate frame. After running this MATLAB script, it produced a plot like this. You can see here the stump surrounded by a lot of points picked up from the ground, and a stump in the background was also picked up. As you zoom in, you can see some of the definition of the stump. You can see a little bit of the indent and the circularity here. From there, I use simple spatial segmentation to filter out all the points from the ground, from the background stump, and other irrelevant points. This produced a final plot that looks like this. This stump comes out to be about 31 inches when plotted. It was measured to be about 29.7 inches in the field. Its diameter comes out to about 15 inches, and in the field it was measured to be about 14 inches. The indent on the side starts at about 19 inches and goes until about 22. In the field, it starts at 18 inches and goes until about 21 inches. The final portion of the MATLAB script that created this filtered 3D point cloud writes these filtered X, Y, and Z coordinates to a text file. This text file was then imported into MeshLab to create the final 3D mesh of the target. Once these points were pulled into MeshLab, it took 2 steps to create the final 3D mesh. The first involved calculating the normal vectors to the points on the target. When calculating these normal vectors, I played around with the number of neighboring points to use to calculate the vectors, and 75 came out to be the most optimal number. From here, I used the Poisson surface reconstruction method to create the final 3D mesh. The mesh that it creates has a lot of noise and a lot of extra surfaces, so I then used the surface selection tool to delete out unnecessary surfaces. And now you can see the final version of the 3D mesh of the concrete stump. You can see the overall cylindrical shape of the stump. You can see on the right there the indent of the stump that occurs. There's still obviously a lot of noise surrounding it, but the Poisson surface reconstruction did pick up most of the cylinder. Thanks for watching my final project. I hope you enjoyed it.